Okay, we're going to use Kirchhoff's voltage law to solve this combination circuit. This is the circuit that we did before, where we broke it all the way down and simplified it, and then we worked back up. But we're not going to do that. We're going to do it a little bit differently. And remember the premise is that if we put directions on the flow here, that the flow is going to be going this way, that the voltage drop through these two resistors and then the voltage drop through these resistors independently are going to be equal to the voltage drop of the voltage source. Okay, so what we do need to do is we do need to simplify this, and we do need to get our total resistance here. Okay, and so if you remember how we did that a minute ago, we looked for series circuits and we simplified these two in series to a single one, and then we simplified these two to a single one, and then we kept going a little bit further, and then we saw that this was a parallel, and we simplified that into our total. Okay, and so when we did that, we saw that these series, which was 470 plus 330, was 800 ohms right here, and that we saw that this one was 560 plus 220, that was 780 ohms. Okay, and then if you recall, then we did the parallel here where we had 1 over our total was 1 over 800 ohms plus 1 over 780 ohms. And so the way that I did that in the calculator is I took 1 divided by 800 plus 1 divided by 780 equals, and then I had to hit the 1 over x right there. And that gave us the 394.94 ohms right here. Okay, so that was we still doing Kirchhoff's, we still had to do that reduction to the our total right here to get that. And the reason why is because we knew that this voltage source was producing 4 amps. Okay, and so we need the voltage here. Okay, so voltage is equal to current times resistance. So if I come and I go with 4 amps times 394.94 ohms, if I take that times 4, I get, if you recall from the last problem, 1,579.75 volts. Okay, so that, because we're doing Kirchhoff's voltage law, we're going to use this voltage so to determine these. So now instead of working our way back up here and looking for series and parallel and working our way back and looking for series and parallel and applying everything, I'm just going to take this voltage that we figured over here. It was 1,579.75 volts, and I'm going to skip this step. I'm just going to bring that voltage right up to here. So up here we're looking at 1,579.75 volts. Okay, so the drop from this node to this node needs to be 1,579 volts. The drop from this node here, or this location here to this location, needs to be 1,579 volts. So we can just take the ratio here. So you can see that if this is dropping 1,579 volts, this 330 is going to drop some, and this 470 is going to drop some. And we can just take the ratio of this. So this whole circuit here was 800. So the ratio of this is 330 out of 800 is what this one is. And this one is 470 out of the 800. So that division gives us the ratio of each one of these that they're going to drop. And so when I get this ratio, it's going to be a percentage. I multiply that by the 1,579.75 volts, and I'll multiply this one by the 1,579.75 volts. Okay, so let's take a look at that. So the first one here is 330, and it's dividing by 800. Okay, so it looks like it's 4.4125. So it looks like this one's going to drop 41% of that voltage, okay? And it's a smaller number, and this is the bigger number, so this is going to drop, you know, probably 58 or 59% because it needs to be 100%. So I got my ratio, and then I'm going to multiply that by 1579.75, and I get this one right here. The voltage is 651.65 volts. All right. This one right here, let's do it again. The ratio, this is 470. So 470 divided by 800, that's my ratio, times 1579.75. And that gives me the voltage on this one of 928.10. And these two are going to add up, and they're going to give me the 1579, because all I did was take the rate, determine the ratio. This was 330 out of 800, and this was 470 out of 800. Let's do this one. So these two were 780. So the ratio for this one is going to be 560 over 800. And you can put the ohms here if you wanted to, because they would end up canceling. So even if these had ohms on them, that's probably better to show that. And I'm going to multiply that by 1579.75. Because from here to here, it's going to drop 1575. This one here, 220. Oh, I'm sorry here. This ratio is 780. 560 plus 220. And this ratio is 780 ohms. So my ratios are 560 over 780 and 220 over 780. So if I go ahead and multiply those out, 560 divided by 780 equals times 1579.75. And I get the voltage drop here of 1134.18. And if I do it right here, 220 divided by 780. And then I'm going to multiply that by 1579.75. And this is going to give me a voltage drop here of 445.57 volts, okay? And so here's my voltage drops through each one of these. And at this point, if I wanted to get current for each one of these, I can, because I have I equals V over R, okay? So I can just take that, I equals V over R, and I can divide these, and I can get my currents. And we would end up with exactly the same numbers that we had on this one that we did prior to when we, you know, simplified it and then backed it up and ended up with everything. So this is just using Kirchhoff's voltage law to get the percentages. And then once again, once you have two of these, in this case ohms and voltage, you can use your power wheel to get current, and you can even get power from the current wheel. You just need two of these, and you can solve for the other quantities. So that's an application to Kirchhoff's voltage law.